We're continuing our discussion of the free particle and a circle. In part A, we have found the solutions of this form and the normalization constants as well as the energy levels corresponding to these solutions. Let's move on to part D. Write the time-dependent wave functions psi sub n plus minus x of t, x and t, corresponding to psi n plus minus of x, and use the symbol omega for E1 over h bar. Okay, so how do we modify our solution to get to time-dependent solutions? Well, we have psi as a function of x and t is equal to psi of x e to the minus iet over h bar. These are the solutions to time in the time-dependent Schrödinger equation. So this is the solution to the time-dependent Schrödinger equation. And let's write the time-dependent Schrödinger equation as well. Minus h bar squared divided by 2m partial derivative, second derivative of psi with respect to x plus potential energy times psi is equal to ih bar d psi del t. ih bar del t is the energy operator. So we have the momentum operator p hat is h bar over complex square root of minus 1 complex number del x, and the energy operator is ih bar del t, and I is square root of minus 1. Okay, so applying these operators, p hat squared over 2m kinetic energy term plus the potential energy operator psi applied to psi is equal to energy operator acting on psi. So we have del psi del t is, as you can see here, minus IE over h bar, minus IE over h bar times psi, and IH bar times del psi del t is equal to, so I multiplied with minus I gives us 1, h bars cancel, so this gives us energy times psi. So the energy levels E sub n are related to the ground state energy. Remember, they're proportional to n square. So it's n equals 1 solution multiplied with n square is how I can write the energy levels. And for omega is equal to E1 divided by h bar. E1 is equal to h bar omega. So we can write the energy levels E sub n as n square h bar omega. So for the psi sub n plus solution as a function of x and t for time-dependent Schrödinger equation, we have the normalization constant a plus, which is 1 over square root 2 pi capital R. Then we have e to the in theta. Then we have e to the minus I energy, which is n square h bar omega t divided by h bar. So these h bars will cancel out so that these time-dependent solutions can be written as psi sub n plus is a function of x and t is 1 over square root 2 pi r e to the in theta, which is x divided by capital R minus, because I have in already here, outside the parenthesis, n omega t. So that's the form of the solution. So let's double check. We have e to the in theta, e to the in x over r, and then we have e to the minus in square omega t, which is what I have from the time-dependent part. And similarly, I can write the psi minus solution. Psi n minus of x and t is the same normalization constant, 1 over square root 2 pi r, 2 pi capital R, multiplied with e to the minus in x over r plus n omega t. Now this is e to the minus in theta solution. So to get this term, you would have plus here. So minus in square omega t. So this will be the solution, the time-dependent Schrödinger equation for clockwise rotation. Let's move on to part E of the problem. Consider the non-stationary state defined at t is equal to 0, but by psi x of 0 is 1 over square root 2 psi 1 plus of x plus psi 2 plus of x. Determine the probability density absolute psi square in terms of capital R omega and t, and simplify your result using the identity 1 plus cosine alpha is 2 cosine square alpha over 2. Okay, so we're looking at the non-stationary solution psi of xt. So let's first write it as a linear combination of these two solutions, 1 over square root 2 psi 1 plus of xt plus psi 2 plus of xt. And that will give us, because we had 1 over square root 2 pi r, 1 over square root 4 pi r. And then we have e to the in theta, so that gives us for n equals 1, e to the I x over r. For n equals 1, we have e to the minus I omega t from the plus solution for n equals 1. And for n equals 2, we have e to the I 2ix over r. And then we have e to the minus, because we have n square here, 4I omega t. So that's in general the linear combination of the two solutions. And the complex conjugate psi star of x and t for this state is 1 over square root 4 pi r, 4 pi capital R, e to the minus ix over r e to the I omega t, complex conjugate of the first term, and then complex conjugate of the second term, e to the minus 2i x over r e to the plus 4i omega t. All right, so we will take the product to get the probability density. Absolute psi of x and t squared is equal to psi complex conjugate multiplied with psi. So 1 over square root 4 pi r multiplied with itself gives us 1 over 4 pi capital R. And then we have to perform this multiplication. So the first term here, e to the ixr, e to the minus I omega t, e to the minus ixr, e to the plus I omega t gives us e to the 0, which is 1 plus, then we move on to the second term, 2ix over r minus ix over r e to the plus ix over r e to the minus 3i omega t. So we will have e to the I x over r e to the minus 3i omega t. And then we have this term multiplied with this term. This gives us e to the minus ix over r e to the plus 3i omega t. So plus e to the minus ix over r e to the plus 3i omega t. And the last term is again 1 because we're multiplying this with this complex conjugate. E to the I0 is 1. And here I note that I will use e to the I theta plus e to the minus I theta is equal to 2 cosine theta. That's Euler's, from Euler's formula. So here I obtain 1 over 4 pi r, 1 over 4 pi capital R, 1 plus 1 is 2, plus I have, this is e to the I theta plus e to the minus I theta, so that is 2 cosine theta minus 3 omega t. This is e to the I theta, x over r is theta, remember, e to the I theta minus 3 omega t. This is e to the minus I theta, e to the plus 3i omega t. So we obtain this situation here. Therefore, this is 2 cosine theta. If I take this into 2 parentheses, you can see here, this 2 will make this 4, 2, and I will have 1 over 2 pi r, 1 plus cosine of theta minus 3 omega t. And to write the final answer, psi of xt absolute squared, I'm going to use this identity. 1 plus cosine 2 alpha is 2 cosine square alpha. So if this is 2 alpha, then I will have 2 cosine square, this thing divided by 2. So I will have 2 cosine square, so 2 divided by 2, I will have 1 over pi r, pi capital R, and cosine square x of theta is x divided by capital R minus 3 omega t divided by 2. That's the probability density function. Part F. With what angular speed does the density peak move around the circle? probability density peak. Okay, so where is the probability density peak? The probability density peak, that's the maximum point, occurs when we have absolute value of psi of x and t square is a maximum. So we have the time-dependent term here, cosine squared. The cosine square maximum is equal to 1. So cosine square theta minus 3 omega t divided by 2 must be equal to 1. So theta minus 3 omega t must be equal to 0 because cosine 0 is 1 and theta is 3 omega t. So what is d theta dt? The angular speed with which the probability density peak moves, d theta dt, is equal to 3 omega. Okay, so this is the angular speed of the density peak. Let's move on to part G. If the particle is an electron and the radius is the Bohr radius, then with what speed does its probability peak move? Okay, so the tangential speed v is r d theta dt. So that's equal to 3r omega. So that is 3r. Omega is E1 divided by h bar. So remember, En is equal to n square h bar omega. So we have 3r over h bar multiplied by E1, which is h bar squared over 2m capital R squared. So these h bars will cancel and I will have v is equal to 3h bar divided by 2mr. That's the speed with which the probability density peak moves, the tangential speed. Okay, now we have an electron. Mass of the electron is 9.11 10 to minus 31 kilograms. We have r is equal to a Bohr radius, which is 0.529 10 to minus 10 meters or angstroms. So this allows us to calculate v. It is 3 times h bar, 6.63 10 to minus 34 joule seconds divided by 2 pi. That's h bar. So we have 2 already at the bottom, so it's 4 pi. Mass of the electron 9.11 10 to minus 31 kilograms. Radius 0.529 10 to minus 10. So this is going to give us a tangential speed 3.28 times 10 to 6 meters per second. Meters per second. That's the answer to part F. Okay. So having the answers from part A, B, and C, first we write the time-dependent wave functions and use the symbol omega for E1 over h bar. So we have the time-dependent Schrödinger's equation where the energy operator is IH bar del del t. The solutions are of the form time-independent solution e to the minus iet over h bar. So, or e to the minus I omega t, some sort of omega. So this is going to satisfy the time-dependent Schrödinger equation. And when we define omega to be E1 over h bar, we write energy levels as n square h bar omega. And then we can put the solutions for psi of x 1 over square root 2 pi r e to the plus in theta or e to the minus in theta, where theta is x divided by capital R, to obtain these solutions. Now we're looking at a particular state, non-stationary state defined at t is equal to 0. And we want to determine the probability density psi x of t absolute square in terms of r, omega, and t, and simplify using this trigonometric identity. So that's what we did here. First, we have written psi 1 plus of x and t and psi 2 plus of x and t, and add them together and take the complex conjugate and multiply them. And when we use this identity, we obtain this result for the probability density. Now we see we have cosine square of some angle, and cosine square is maximum when the angle is 0. So that means theta minus 3 omega t is 0, or theta is 3 omega t, or d theta dt is 3 omega. So that means this is the angular speed of the density peak. The density peak occurs when theta is equal to 3 omega t. That's the maximum extremum point. The first derivative must be 0, or this must be a maximum. The maximum is, for cosine square, 1. And then in part G, we were asked to find the speed with which the probability peak moves, not the angular speed. The speed is r times the angular speed, d theta dt. So d theta dt was 3 omega for the density peak, so it's 3r omega. And for omega, we have E1 over h bar. So we obtain this result for the tangential speed. And we can substitute the mass of the electron, the radius of the Bohr radius, radius of the hydrogen 1s orbital, and h bar values to obtain 3.28 10 to 6 meters per second as our final answer.